Okay, so now we'll talk about cubic spline interpolation. So this is an example of a piecewise polynomial interpolant where when you restrict to each subinterval, you have a cubic polynomial. So let f be defined on some interval a to b, and we partition this as follows. So a is x0, which you have a sequence of xi's in increasing order, and xn is b. So the cubic spline interpolant of f over this partition, okay, is a function s of x, okay, defined by the following. Okay, so for the first thing is that on each subinterval, xj plus 1, right? S coincides with a cubic polynomial. Okay, so S of x is equal to S sub j, which is aj plus bj x minus xj plus cj x minus xj squared plus dj x minus xj cubed. Okay, and this is for j equals to 0 to n minus 1. So that's the first condition. The second condition is that S interpolates f. So S at xj is equal to f at xj, and this is for j between 0 and n, including the endpoints. Okay. Then the third condition is that S is continuous. So S j plus 1, xj plus 1 is equal to Sj xj plus 1. And so j is between 0 and n minus 2. Here, and then the fourth condition is that S prime is continuous. So Sj plus 1 prime at xj plus 1 is equal to Sj prime at xj plus 1. Again, j is between 0 and n minus 2. And then the fifth condition is that S double prime is also continuous. Okay. All right. So S double prime j plus 1 xj plus 1 is equal to Sj double prime at xj plus 1. And again, j is between 0 and n minus 2. All right, so let's do a little bit of a dimension count here, right? So we have at each subinterval a cubic polynomial. So a cubic polynomial has 4 degrees of freedom. There are n subintervals, okay? So there are 4 sort of unknowns per subinterval. there are n subintervals. So that implies there are 4n unknowns. Okay, and then you have a bunch of constraints. So the first set of constraints are the interpolation condition. So the interpolation condition has n plus 1 conditions. The continuity conditions each have n minus 1, n minus 1 conditions, n minus 1 conditions, n minus 1 conditions. Okay, so that sums up to 4n minus 2 conditions. Okay, so you have 4n unknowns and then 4n minus 2 conditions. So you can observe that you need 2 more conditions to close the system. Right. Let me perhaps give you possible examples of those boundary conditions, and then we can talk about how to solve the corresponding system of equations. Okay, all right. So we need 2 more conditions, which are typically some sort of boundary condition. Okay. So these are some possible ways of closing those conditions. The first of which is what is called the clamped or complete cubic spline. Okay, and essentially it's like that involves prescribing S prime at A, which is say F prime at A, and S prime at B, which is F prime at B. Okay, and you use this clearly if you happen to know what the derivative at the endpoints are. Okay, the second of which is what is called the free or natural cubic spline. Which is a condition that the second derivative at the endpoints vanish. So the problem with this is that it introduces errors which are big O of h squared near A and B. Okay, so this is not always recommended. Okay, and then another possibility is what's called a not the not condition. So not a not. Okay, which is that S triple prime is continuous at the interior points which are closest to the endpoints. X1 and xn minus 1. Okay, and you can use this clearly if you don't know what f prime is at A and B, right? So you use this if f prime at A and f prime at B are unknown. Okay, so So let's think a little bit about it. Again, the clamped cubic spline is what you might use if you happen to know the derivatives at the endpoints. The not condition is something you could use if you don't know the endpoint conditions, because all it's really doing is saying that, at the points x1 and xn minus 1, you have a little bit more continuity in the higher derivatives than you otherwise do elsewhere. Okay, but you're not really sort of prescribing any strange data, whereas the free or natural cubic spline is somehow, it's like imposing quite a stringent condition. It's like this is something you don't necessarily know the function f satisfies. So so you can introduce, it's like an order h² error. It's like close to those endpoints if you choose that. Okay. Anyway, so those are some possible boundary conditions which then close the system of equations for the cubic spline. Okay. And the next thing we're going to do is that we're going to try to set up the system of equations for this, and then we'll revisit these boundary conditions and say what kind of conditions they have on the coefficients of the cubic splines in the interior. So let me stop for now.